Hello and welcome to another video. In this video we're going to be working on find largest value in each tree row. And in this problem you're given the root of a binary tree and you want to return an array of the largest value in each row. So basically you want to go like row by row and find the largest value. So here it would be 1, 3, and 9. And in an array of 1, 2, 3, you would want to have 1 and 3. And so this problem is actually very easy if you know how to do like a basic DFS or a BFS, either one. And all you have to do is you just do a DFS. So DFS, and we just simply pass in the current level we're at. So for, the root will pass level 0, and then for each recursion, we'll just add 1 to the level. And so what that's going to look like is if we have some result array, we're going to start at the root, and we're going to say, okay, we're at level 0. So this should be at index 0 in the result array. Do we have an index 0 in the result array? Is it long enough? And if not, let's just throw the number in. So right now our result array is empty to start off, right? So it'll start off as empty, and we will just put in 1 because there is no level 0, so we can just check the length. So if the level you're on, basically, if level equals length, then add the value. Otherwise, maximize value at level. And let's kind of show what that's going to look like. So here we're going to add. Then we will recurse down. So here we're at level 0. So we will recurse down here. And we will be at level 1, right? So these are both level 1, level 2, level 2, level 2. So at level 1, we're going to check, do we have a level 1? No, because our array is only length 1. So we will just add the 3. Then when we get to this node in our DFS, obviously, like, depending on the order you have this essentially, but when you get to this node, you'll say, okay, well, is there something at node 1? Yes, there is. Is 2 greater than 3? No, it's not, so we'll keep the 3. Then for this value, we're going to say, is there a level 2? No, there's not. And what's going to happen is you're going to get to these values left to right, but the order doesn't even matter because you're literally just trying to maximize. It's like a very easy problem, in my opinion. It's almost like an easy problem. Like if you could just do a DFS or a BFS, like literally anything works here. So essentially, we're going to get to 5, and we're going to say, okay, well, is there a 5? Or is there a 5? Is there anything at level 2? No. Let's just add the 5 in there. Then when we check the 3, we'll say, okay, there is something at level 2. Is 3 bigger? No. Let's keep the 5. And then we'll get to the 9, and we'll say, okay, is there something there? Yes. But is 9 bigger? Yes. So we will replace it. So essentially, all you have to do is at every node, the level you are at, you just check, does that level exist? If not, add it. And otherwise, just say, whatever's at location is the max of whatever's there already or your current value. And that way you will grow your array proportionally to the tree, so you don't have to know the size of the tree. You're basically just appending one value at a time. And the way, like, no matter what traversal you have, you're never going to be at a level that's like multiple levels down, right? So you're always going to be at a level that's just after the one that you have because you're going to be traversing down. So if you have like level 1, you won't have level 2 and so on. You're never going to like be at level 10 without having a bunch of other levels filled the way a DFS or a BFS works. And that's literally pretty much it to this problem. So there's literally just a straightforward DFS, keep track of the level, and just maximize the value in the array at the level. Very easy, and let's code it up. So we're going to have a result array. We'll just set it empty. Then we'll say def DFS of a node and a level. And we'll say if not node, if the level doesn't exist, let's just return. Do this. Then we have to say if level equals res or length res, meaning like for example, if we're at level 0, this will equal the length of the result. That means there is no value there, right? So if there is no value there, let's just append it in there. So res append node.val. Else res at that level, right? The level is the index that we should be checking, equals the maximum of whatever's there already and the node's value. And then we just simply have to DFS node left, level plus 1, and DFS node right, level plus 1. So as long as you've done like this kind of DFS before where you keep track of the level, super easy, the order doesn't matter, you're just min-maxing. And then we simply have to call DFS at the root with level 0, and return the result. And that is pretty much it. So very easy problem. Let's take a look. And there we go. And yeah, so you can see it's pretty efficient. And now let's talk about the time and space. Oops. So for the time, this is gonna, we are gonna visit every single node, right? So we're no matter what, we're visiting every single node pretty much. So that's O of n, where n is the number of nodes we have. And then for the space, if we don't count output as part of our space, which we shouldn't, because that's totally separate, we're keeping the minimum number of variables in the output we can, right? The result array will never be bigger than what we're outputting. We're never making it too big or anything. So the space is basically the I guess you can. So usually I say it's O of n, but you can also say it's height of the tree. Either one is acceptable, because if you go back to this picture, basically the space depends on the height of the tree. So if you have a tree like this space would be O of n, and it would also be O of the height of the tree, because the height of the tree is very big. But if you have a more balanced tree, it's more like this, and so on. So on average, log n, worst case, O of n. I guess you could say it's O of height of the tree or O of n. Either one's fine. But just pretty much every single recursive tree problem that you don't have balanced trees, space is always going to be O of n, and time is pretty much always going to be O of n as well, unless you're doing some other stuff because you have to check every node. But yeah, that's all for this problem. Pretty easy one. So if you did like this explanation, please like the video and please subscribe to the channel. And definitely this is one that you should be able to you should be able to do this one fairly straightforwardly. If you've never done it, I would definitely practice a few times, because I don't think there are too many easier problems than this, other than just write out a DFS of a tree or something. So all right, that's gonna be it for this one, and I'll see you in the next one. Thanks for watching.